Hi all, and thank you for having me. So I'm going to talk today about network automation architecture and design-driven automation. I've been asked to combine two talks, so you're getting two for the price of one. A little bit about me. So my name is Przemek Rogala. I'm an automation architect at Network to Code. We design and provide network automation platforms, and we do network consultancy. And those talks today are based on solutions that we provide to a lot of our customers. So this is all based on real life problems and how we solve them. So I'm going to start first talking about network automation architecture and why do we need it and what is so great about it. So if you've ever dealt with network automation, you probably noticed there are a lot of tools out there, open source ones and commercial ones, and it's very difficult to choose one. Like, what are all of those tools doing? Well, it's really easy to get overwhelmed and confused. And let's not forget that our goal is not to play with the tools. I mean, a lot of them are really shiny and cool, and we like to play with toys, right? We are engineers, but the end goal is to solve a problem. And that problem could be anything from provisioning a switchboard to an entire data center, to creating a VPN between your on-prem and cloud, or whatever else you need to solve in your own business domain, right? This is our goal. This is what we need all those tools for. And this is where network automation architecture can help us. By having a reference architecture, we can define functional blocks that we will use when we build our solutions. And this reference architecture, as you can see, is relatively simple. It's got just 6 building blocks. Main one of them is actually something you already know, and that's your network that's your network infrastructure, be it physical devices, or virtual ones, or even cloud resources. And then we have 5 functional blocks. And we start with user interaction. And this depends on the type of your user, right? This could be chat ops for maybe your NOC engineers that want to interact with your network devices, find out what's going on. Or it could be your ticketing portal. Or it could be something like dashboards when you want to check operational state of your network. Then we have a source of truth. This is the central point of our architecture. In modern network automation, we use source of truth to store the intent. This is the desired state of our network. How do we want our network to look like? And this is where we have our device inventory, our IPAM data, locations, anything related to data center, essentially anything that you need to configure your network and to express its desired state. And then we have automation engine, right? So our source of truth is what? What do we want it to look like? Automation engine helps us in doing how. How do we get this state and we apply it to our network infrastructure? So this is a very, very important component. And once we've applied this, once we've configured our network infrastructure, we have a telemetry and observability. So we need to find out what is the operational state and compare it to the intended state. Do those two match? So it's very important that we have this component in place. And finally, we have orchestration. Orchestration provides us with workflows, and it takes advantage of all the other blocks, functional blocks, and it can have multiple tasks stitched together. So you can get data from source of truth, it can trigger automation engine to do configuration, and it can close the loop by querying our telemetry data and finding out if the desired state matches the state that's on the devices. And if it's not, it can trigger another task to remediate that. So this is a very simple network architecture over here in front of us. And now I'd like to show you an example of a manual workflow that you might be familiar with. And we'll tie this to our network automation reference to see how we can use that to build automation workflows and how we can turn something that is frankly quite a chore and shouldn't be done by engineers into an automated workflow. So this simple example, as you can see, is something that's commonly found out there. A network services provider sends a maintenance notification. Circuit is going to be going down in a week from now. We have an engineer that looks at, maybe it's an email or whatever else it is that he got from our service provider. He passes that, updates the system, puts that into calendar, notifies the groups. And it's frankly not what we should be having our engineers do, right? This doesn't provide any business value. And worse yet, if service provider changes their mind, they update the notification, we need to go through the process again. So this is not great, right? We don't want to be doing that. This is what we have network automation for. So what we can do is we can look at that manual workflow and identify tasks that we can automate, right? We want to split that into individual tasks and apply automation to it. So this is essentially one-to-one translation of a manual workflow. We have a maintenance coming from the service provider, and in the first task, instead of having an engineer look at it, we have an automated process that gets that data, normalizes it, because often this is a free text. It's very difficult to find out what actually is in the notification. So we want to normalize it and put it into structured data. Then we validate it against our source of truth. Is that circuit that's mentioned in the maintenance notification actually in our database? Do we have a device connected to that? And if we do, we validate all of that and we record in our source of truth, right? So that maintenance is no longer out there just on calendar. We actually have in a source of truth connected to the circuit that will be going down. And finally, we have automation sending a notification out. So in this simple automated workflow already provides a value. There's no engineer involved here, right? This all comes in through the automated system, gets recorded for future consumption. We save time. But that's not all. Now that we've automated this simple workflow, we can enhance it. We can use data in SOT to do a sanity check. Is the pop related to the circuit going to go down if a circuit is under maintenance? Maybe we already have some other maintenance happening at the same time. How about the data in the actual requests? Is the start date before the end date? You never know what service providers will send to us. But then we can go even further. We can have an orchestrator notify our engineering team that maintenance is about to start. It can automatically drain the traffic from the POP, shut down BGP sessions, and after all of this is done, it can run synthetic checks. So this is our telemetry bit, right? It'll check that once the circuit is back up, the traffic is actually flowing across it. All of that is automated, right? No one needs to go in and check it. And once we confirm the traffic is flowing, we just bring all of our BGP sessions back up. So we talked about the workflow, and now we can go back to our architecture. All of the blocks we talked about, all of the functional blocks, we now can map all of those tasks onto the functional blocks to help us inform how we will design this workflow. Like, how are we going to implement all of this? So see all those tasks over here: data normalization, validation, checking if circuit exists, is it connected to a device? That's our source of truth, right? All of our data is already recorded. And also the data related to maintenance will be recorded in source of truth. Then we have our automation engine. So automation engine will be used to bring sessions back up after and drain the traffic and shut BGP session down before the maintenance starts. Then we have our user interactions, right? So we're going to be sending notifications to our engineering team saying maintenance is about to start and maintenance is over. And for our synthetic testing, we have telemetry and observability, right? This will run the test and will confirm if traffic is flowing. And finally, for user interactions, as I mentioned, we will have notifications that are being sent. And then we have orchestration, which is what actually is kicking all of those workflows and running tasks. So we've now mapped this workflow onto our architecture. And now we're going back to our tools. So at the beginning, we had this screen with a lot of different tools. And it's not very easy to find out what all those tools are doing or what functionality they provide. Or even after you find out, all right, I know what this thing is doing, but how do I use it? Like, how do I map it? Do I use all of those 10 tools or do I just use one? But now we've got those functional blocks, we can decide what tools to choose. We can use Autobot, an open source SOT sponsored by Network to Code, to store all of the intent data, our device inventory, our IPAM, IP addresses, VLANs, everything related to the intended state of a network. Then we can use Git to store the configuration templates that will be used to configure devices. So how do we take the BGP session down? We take intent, run it through that template, and we feed it to the automation engine. We could choose Ansible, a very popular choice with a support for a lot of different types of platforms. And since we chose Ansible, a very natural choice for orchestrator will be AWX, which uses Ansible templates Ansible playbooks under the hood. Finally, for telemetry analytics, we can use telegraph collectors to get data from network devices, the operational state via SNMP or streaming telemetry, and Prometheus, a time series database where we store all of this data and we can use it to efficiently query the state that we've collected using collectors. And at the end, we have our user interactions. We could use Matemos, which is an open source messaging platform, and we have Grafana for dashboards. So all of this telemetry data that we're retrieving, we could create dashboards for our end users where they can see the state of a network before and after. And our orchestration can also use dashboards and data coming from Grafana and TSDB to close the loop, to confirm if the desired state matches our operational state. So this is what a network automation architecture gives us. It gives us functional blocks and relationships between functional blocks to allow us to reason about network automation, about workflows, and allows us to take all of those different tasks and map them onto functional blocks. So when we talk to our network engineers, we talk to our architects, we could use this reference and everybody understands. It's like in programming, right? We know about modules, we know about classes, we know how to do all those things. So having architecture, a good network automation architecture, and this is not the only one, this is just a reference that we use generally, but I know our network automation forum is working on one, which will be even more agnostic and will be released sometimes in the near future. But what is important is that having this architecture in place really makes things easier for everyone, and it makes it easier to choose the right tooling for the job you need. Okay. So now that we've talked about network automation architecture, I want to move on to another topic that was briefly mentioned yesterday during yesterday's sessions on network automation blueprint, and that's design-driven automation. From what I remember, design-driven automation was marked down on a few different categories. I think one of them was complexity and maybe difficulty of getting started. And maybe that's not entirely untrue. But what I think matters is that this is pretty much the only approach we now have to manage complexity emerging from our modern networks. As we go through automation activities, as we start with very simple tasks that we can probably use some simple scripts to automate those. But eventually we get to the point where we need to create hundreds, maybe thousands of data points for one service. And we need to somehow connect this. And that's the point of design-driven automation. We have all this data, and that data is not connected right now. Right? We create all this data in the source of truth, we deploy the automation engine, but we don't always know what was connected to what. So the question, does interacting with your network spark joy? We have a lot of different user types interacting with our network, not just network operators, right? We usually think of network operators when we think of, who needs to use a network? But there are end users of a network, people who need to do something with a network in order for the app to work. I need to provide some software to business, and it runs on top of a network. But most of the time, when I try to get something out of the network engineering teams, it takes ages, and I don't really understand what I'm asking for. So the question is, how do your users interact with a network today? Do they know what they want? If they know what they want, do they know how to ask for it? And even if they know how to ask for it, can they go and self-provision? It'd be nice if we had something like what cloud providers offer, right? Some kind of portal where you go, you search for the thing you want to do, you provide a minimum amount of input, and just say, I want this app to talk to this app. And I don't know what's in between, and I don't care. I just want all of this to happen. I click a button, that thing gets provisioned, and I don't have to tell you, provision this on 25 firewalls. No, they're not interested in that. And the problem is, right now, often we get requests via ticketing system, or maybe someone comes around to our desk and tells, mate, could you give me access to this or that? Right? And you just write it down somewhere, or you look at the ticket, and you have to translate it, right? You have to translate it from the user request to what needs to get provision on the network, right? And often something gets lost in the translation. You misunderstand what they asked for. Or maybe you forgot this very important step, this one dependency, and the thing doesn't work. You get it delivered, the data that backs up whatever they ask for, it's not connected, right? We lose all of our context when we do translation. And that's the problem. We have our wikis, we have our drawings, we have our runbooks that we follow to do all of this. And that data was connected to begin with, implicitly, right? Because it's all connected to a service, to something that needs to be deployed. But as I mentioned, for some of those services, there could be hundreds of data points, maybe thousands. And once we put it into SOT, this becomes very difficult to manage. And don't get me wrong, SOT is very important. It's very important to record all of our data and have it in one place. But when we don't create some kind of connections, we lose the context. We don't remember why we added something last month, a year ago, right? All of that gets lost. So, what do we do about it, right? So here's an idea. Could you, take parts of your network, the bits that provide value, and turn them into a product, right? So could you offer a service? And that's the idea behind design-driven automation. When you hear design, think service. Design a service, right? And how many services? It honestly doesn't matter. You could start with one. What matters is that we need to turn network, and not all of a network, just the important bits at least for now, the bits that matter to our users, turn that into services, easy to use services, and services that work well, something that users will be happy with. And we need to remember that all of this needs to be simple. So simplification is the key. And it's not simplification for us, network engineers and architects, right? We still need to do validation. We still need to do API integrations and design and put all the logic in place. All of it is complex, and that's not going away. But our users don't care. They don't need to know that. They want something simple that they can use. Because otherwise, you will feel the pain. They will feel the pain, but you definitely will as well. They'll come to you, they'll complain, and they'll complain again until you make it simple enough to use and you make it work well. So that's the idea here with design-driven automation. But we have all of this data that results from the requests being translated. We need to connect the data. When it goes into the source of truth, we need to record relationships. That data needs to be connected to the service. And services can change, right? So we start with version 1 today. A month from now, we add another attribute. And we have version 2 of a service. And those services need to coexist, right? You won't necessarily go back and update all of those services. So you need to know that data is connected to service, but what version of that service? Protected. That's a very important word here. And what it means is that data connected to the service cannot be changed by just anyone, right? On a network of any decent size, we'll have hundreds of thousands, millions of data points. But only a subset of our data, in most cases, will be connected to a service, right? And then certainly just a single instance of a service. And we can't allow anyone, just anyone, to go into our source of truth or even any other process and change that data, because then you change the service implementation, right? Next time your service runs and your provisioners kick in, and if they want to check if the service that's deploying the devices matches what's in source of truth, that will get changed because someone went into your source of truth and updated by one data point that shouldn't have been changed. So you need to protect your data. And finally, we need to follow data lifecycle. From the services creation, when data gets entered into SOT and connected to the service, through the updates to the service, because the user goes back and actually says, oh, no, I didn't want to deploy it to this device, I actually wanted a BGP session on this device. So service needs to update it, right? The process needs to kick in, but it's still the same service instance. And finally, when the service is no longer needed, we want to decommission it. And with it, we want to decommission the data. We no longer need it. So what are those services, right? It could literally be anything. It could be a branch side deployment, a top of rack deployment in your data center, or literally creating a completely new data center. It's up to you what you want this service to be and up to your users, right? If your users come to you and keep asking for the same thing over and over again, that's probably a good indicator that this is something that should be turned into a service. Start with something small, something that's maybe easy to achieve, and something that will provide value very quickly. And now the question is, how do we do it? So this is an example of how you could reason about and abstract what we want to do. We start with service catalog. This is kind of like a portal, right? Where like what cloud providers do. You go in there, you maybe have some kind of categories, or maybe you just do a search, and you find a service that you're interested in. And those services, we could roughly split the way they build into 3 different blocks. And that's our inputs. And those inputs is what users will put in when they request a service. The fewer the better, right? You don't need to expose all of the inputs if they're not required. In fact, you shouldn't. If all the user needs to tell you is that he wants a connection between app A and app B, and you can figure out the logic, only offer 2 inputs and validate those inputs. We shouldn't allow users to put something that's illegal, because what's the point? Right? We're going to have to tidy it up later. So if it's wrong, refuse, deny, and tell them what's wrong. They need to know that what they put in maybe does not conform to some standard. They need to update the name because it's missing 1 digit at the end of it, because that's your standard. Then we have a template. Our template could be Jinja 2 or Python or Golang. It doesn't really matter. What matters is that you will take the definition of a service and you will create a plan that will be used for creating the data later. So at this point, this is just an abstraction. So we have to do some kind of translation. It's similar to configuration templates, right? We take something abstract and turn it into something less abstract, but we don't create a data yet. And then we have context. We don't operate in a vacuum. In addition to our network, there are some other things out there like ticketing systems, compute resources that need to be reserved. So we need to take that into account when we build our services. And then comes the time when a user comes in, goes into a service catalog, finds the service they want, and they click Run button. And all of this gets fed into a renderer. And renderer will create a plan. So again, at this stage, we don't actually create the data yet, but we'll create a plan with abstraction, but lower level abstraction, of what the end data will look like, given all those inputs, given the template, given the context. And that plan will be fed into a builder. And this is a very important component where there's going to be a lot of logic. And that logic will decide what data needs to be created, because maybe this is a second instance of a service run. User just changed 1 thing, and builder needs to decide that we only got 1 data point that's different. So when we go and generate that data, we don't need to create thousands and thousands of data points, we just need 1 object. Or perhaps user decided to decommission the service. That's going to be sent into builder again, and builder will be responsible for deleting the data. So at this point, we get data that's actually created, for instance, in our source of truth. And this all constitutes a service instance, right? So now data gets connected to a service instance. And we can start our automation. We can actually kick Oracle workflows that will use the data behind the service to provision it wherever it needs to be provisioned, in clouds, on our physical devices. And we go back to our network architecture. So you can see we simplify this a bit to get rid of some other things, because they already imply in the service data, right? There was already an input when user came in and asked for a service instance. We already have all of the data. So now with all of that data, with all the intent, we can just pass it on to the orchestrator. An orchestrator is going to go trigger our automation engine, which will go to however many devices it needs to go, 10, 20, 30. It's like with a netcom, right? When we have network-wide transactions. It will make sure that all that service data gets affected onto our network infrastructure. Our network infrastructure gets configured, And we go back to telemetry and observability. We check the operational state, and we close the loop. We check if what's been deployed matches our service definition. And if it doesn't, our orchestrator can remediate it, right? We can enter the process of reconciliation. So this is how we can connect design-driven automation to network architecture. As you can see, it's all connected and relies on each other. And you might think, okay, that's all great. You know, the hyperscalers, they do it because their environments are uniform. They have economies of scale. They have well-paid people, right? But truth is, you can start with something small. Just look at one simple service that can provide a value. And just like in finance and investing, leverage the power of the compound interest, right? You start with a small service, maybe add some more enhancements to that service, then you build another service. And before you know it, from a year from now, you'll have 20, 30, maybe 50 of those services. Your users will be happy and will come back and will ask for more of those services. So it's not just for hyperscalers. Anyone can do it. But we shouldn't forget testing, right? Whenever you do your network changes, you've got some verification steps. It's no different with designs, except here we can do it much earlier, right? Because we can do synthetic testing, we can follow the CI/CD pipelines, we can use tools from the world of programming, and we can ensure that our inputs are validated, right? We could create tests for those. We can ensure that data that gets generated when the service is requested is correct. It is very important, especially in case of our designs and services, where we test it thoroughly, because those will be self-service, right? So you might not even know that thing just kicked off on your network, and you don't necessarily care. But you need to ensure that this is rock solid, because then you'll make sure you won't have any issues on the network, you won't have to go back and roll it all back. And in order to realize this vision, you need to break your network into a collection of module services. And don't think that you can only do it with your greenfield network, right? Hopefully, your existing network, when you build it, followed some kind of designs, right? You had some blueprints. So you can go back to those, and you can codify those and start bringing them back into this world of design-driven automation. You can put it all back into source of truth. You can connect it. And again, start small. Start with one design. And for any future services, begin with design-driven automation, right? Don't try and retrofit it later. You obviously do it for the brownfield, but for greenfield, just try and start think in those terms. Try and make it all into services. Right, and just to show you that this is not just a theory, I do have a short demo to show you, which hopefully will work. And this is a concrete implementation of this idea of design-driven automation using something called Design Builder, which is built on top of our platform Notobot. And as you can see over here, we have a list of different designs that I created ahead of time. And what I want to do is I want to provision a new POP, right? So I'm going to go here, and I'm going to trigger this design creation. So we'll have some deployment name. I'm going to call it BalticNOG. There you go. POP. And POP name, gonna do VNO. Right? And we're gonna choose size small. As you can see, a minimum amount of inputs. Only things that are necessary. What does small mean? Well, user probably doesn't really care, or maybe it's explained somewhere in the service catalog. The point is, they don't need to specify how many switches, how many routers, whatever else in between. They just choose small. There's some other options, right? But all they need to know is small. And we run this job. And look, there's a problem. We have a certain expectation on our network. The POP name has to include digits afterwards. So we go 3 letters followed by digits. So this is our input validation. We've applied this principle here. So I'm going to run it now. As you can see, this just kicked off and automatically created a number of objects. So we're creating things like location, manufacturers, racks, device types. roles that those device types will have. You know, a number of objects that would be really cumbersome to create by hand and would be next to impossible to actually reason about later and connect to. All of the devices where we just deployed, all of that is here in one place, tied to these specific designs. And now that I've got this design, I can run another design on top of it. And in this case, I will create a point-to-point connection. Specify device A, and I specify device B on the other side. See, and we're running another design. So we are provisioning another service, minimum amount of inputs. And we create a connection, IP addresses, connected it all. And we can see all of this in our design deployments. And if I'm no longer interested in this design, if I don't want to see this anymore, I can decommission this design. I could go in here and say, yeah, this is no longer needed. And a process will run, and it will automatically remove all of those objects. And just to show you one last thing, if I go to things that have been created by the first design and have a look at one of the devices, see there's a tab called Design Protection. All of those attributes are connected to a service deployment and they are protected. Nothing else can go in and change this. If you're trying to do it, it won't allow you. So that's it. That was my demo. And that was design-driven development and network automation architecture. If you want to learn a bit more about network automation architecture, we've got a series of blog posts on Network to Code blog. We have a chapter on network automation architecture in Network Programmability and Automation book. It's been written, among other people, by founder of NTC, Jason Edelman, and my friend Christian Adel. If you want to learn about circuit maintenance automation, we have an app where you can install in Autobot. There have been several presentations showing how that works, and it's all available on GitHub. If you want to learn more about design-driven automation, there have been excellent presentations on that topic already, one from Jeremy Schulman and one from Wim van Jun. And also, if you want to take it for a spin and you want to have some more hands-on experience, my dear friend Nikas ran a test-driven design workshop at AutoConf 3. That's also available on GitHub. So you can clone it and play with it locally in your environment. Finally, I've included some example tool references, things that we talked about. All of them are open source. You can download them. Most of them will be on GitHub, if not all of them. And that's all I had for you today. Thank you very much. Hope you enjoyed it.